Hello guys, and welcome to today's video. I am going to introduce us to the common Laplace transforms you should know for engineering mathematics. Now, before I go into this video, I want to tell you that I am not here to teach you Laplace transforms like from the first principles. I want to assume that at this level you already have some knowledge about Laplace transforms. So I'm just going to point out the most important Laplace transform formulas you need to know, and one or two examples, so that when you encounter problems in engineering mathematics or in control system theory, you could be able to use these Laplace transforms. And you should always have these Laplace transform formulas that I'm about to show you on the tip of your fingers, and trust me, you are going to be okay. So why don't you sit back and let's dive in. Now, the first thing that you need to know is the definition of Laplace transforms from first principles. Okay, everyone should know that. So by definition, from first principles, the Laplace transform of a function f of t is defined as this integral, exponential integral from 0 to infinity, and you have your f of t multiplied by exponential minus s t dt. Now, this variable that you're seeing here, which acts as a constant in this integration, is what we call the Laplace variable s. So Laplace variable is popularly and most commonly denoted with a symbol s. So that's our Laplace variable. So this is Laplace from first principles. So I will try as much as possible not to carry out any integration on first principles. So you should know this, okay? And this is our manual. This is everything that we need to know. This is the key to the Laplace transforms, and from this particular definition we came up with a couple of Laplace transforms for some functions. For instance, let's say the Laplace transform of 0. I'll start with some basic functions that you should know. The Laplace transform of 0 gives you 0. The Laplace transform of 1 gives you 1 over s. Okay, you should remember this. The Laplace transform of c itself gives you 1 over s squared. And what else again should we know about some basic functions? The Laplace transform of t raised to the power of n, generally, that's t raised to the power of n, it gives you n factorial divided by s to the n plus 1. Okay, so you should know this, that the Laplace transform of t to the power of n gives you n factorial over s to the n plus 1. So this is about functions, let's say linear functions or non-linear functions in this particular form t. So when you are asked to find the Laplace transform of t squared, t cubed, t to the power of 4, or even 1, or t, you should know the answers. Is that okay? So I'm going to give us examples, but let's continue listing out the functions. So this is for polynomials. So let's go to exponentials now. So when we are talking about exponentials, the Laplace transform for an exponential a is any arbitrary constant. So this gives me 1 all over s minus a. Okay, so if a is positive, then you have s minus a. How about you're finding the Laplace transform of exponential minus at? Then you're going to get 1 all over s plus a. So in general, the Laplace transform of exponential plus or minus at is going to give you 1 all over s minus or plus a. Is that okay? S minus O plus A. Remember, in putting the A, I did not include T. So it's a common mistake that some of us usually make, and you find yourself trapped. So the expression here is devoid of T. So basically what Laplace transform does is that it converts a function from the time domain. So Laplace transform converts from time domain to frequency domain. So in time domain the variable is T, but in frequency domain the variable is S. And for most of you, you will know that S is something like an alpha plus j omega. Okay, so this is the actual depiction of this variable S. For those of us that are into control theory, electrical electronic engineering, S is alpha plus j omega. This is an attenuation value. Alpha and omega is trying to tell us like an angular frequency. Okay, so I'm not going to dive much into that, but I'm going to dedicate a special video later in the future to explain Laplace transform in full. So just because we want to apply Laplace transforms to engineering mathematics, I'm not going to do all that here. So I'm just trying to tell you the basic Laplace transforms you should know. So this is exponential cases, then you should know about this one. Then another Laplace transform that you should know is the one for trigonometric functions. So for trigonometric functions and perhaps hyperbolic. So I want to find the Laplace transform of sine 8t and the Laplace transform of cos 8t. So I already know the answer, but I want to just do a little fancy derivation for the Laplace transform of sine 8t and Laplace transform of cos 8t. So those of us who are good with complex numbers will recall that we can represent an exponential complex number in this form from complex number theory. Exponential I theta is cos theta plus I sine theta. So sometimes theta is represented as omega times t. Okay, so let's say we have exponential I omega t. You have cos omega t plus I sine omega t. So this omega is just a value that depicts the angular frequency or angular velocity, and that is usually that value that you see here or here. Okay, so now this is Euler's representation of the exponential complex number, exponential I theta. You can represent it in terms of a cosine value and a sine value. Okay, so it's a complex number because of I, which we remember as the square root of -1. Now if you want to use this method to determine the Laplace transform of cos cos omega t and sine omega t, or cos 80 and sine 80, you need to take the Laplace transform of both sides. So exponential I omega t is equal to the Laplace transform of cos omega t plus I sine omega t. Now Laplace transform exhibits a property called linearity. So linearity allows me to see the Laplace transform as the sum of some function, as the sum of the individual Laplace transforms, like this: the Laplace transform of cos omega t plus the Laplace transform of what? I sine omega t. And permit me to go one step further before I start solving. The Laplace transform of exponential I omega t will still evaluate to the Laplace transform of cos omega t plus. So because of the property of linearity, any constant can come out from the Laplace transform. Okay, so you have I Laplace transform of sine omega t. So our objective is to find the Laplace transform of cos omega t and the Laplace transform of sine omega t at once. So we are going to do that like this. So if you consider this left hand side, the Laplace transform of, we should recall that the Laplace transform of an exponential at is 1 all over s minus a, right? You remember. So I'm going to apply it to this hand and you will see the amazing results that we'll get. So the Laplace transform of exponential I omega t is going to be 1 all over s minus, the whole of this is acting as a when you compare it with this one, so you have I omega. Is that okay? So what do you do from here? So you have that the Laplace transform of exponential I omega t gives me 1 all over s minus I omega. You can rationalize, so you have s plus I omega divided by s plus I omega. So why am I rationalizing? I'm rationalizing because this I is a surd, but it's a complex surd. Okay, root minus 1. So that's why I'm rationalizing. So when we rationalize, we get s plus I omega divided by this looks like the difference of two squares to me. So you're going to have s squared minus I omega all squared. Okay, if you remember difference of two squares. So to round it up, Laplace transform of exponential I omega will now be, so you have s plus I omega divided by, so remember we have s square minus, so I'll have I square and omega square from this place according to the law of indices. So this is s plus I omega divided by s square. Now I square in mathematics, I square, where that's I, this is I, if you square both sides, so you have I square to be minus 1 because this 2 cancels out the roots, just like we normally like calling it, right? So I square is minus 1, so you have minus minus, okay, and it gives you a plus, and this is omega square. Now if you split this, you're going to have what? S divided by what? S squared plus omega squared, then plus I, then omega divided by s squared plus w squared. Okay, so you just applied the rule of like partial fractions somehow when you have something plus something over a common denominator, so each numerator can take that value of our denominator. Is that okay? So if you compare what we've gotten now from the beginning, Laplace transform of exponential I omega, we got the Laplace transform of exponential I omega to be cos I omega t. Sorry, I missed the t, so you shouldn't miss the t. I omega t. Laplace transform of exponential I omega t is cos omega t plus I sine omega t, and now we've gotten it as s all over s squared plus w squared, then plus I, you have w all over s squared plus w squared. Now you agree with me that we said this is also the Laplace transform of, sorry, like this, then the Laplace transform of this one over here. So this was what we established right from the beginning, that the Laplace transform of exponential I omega t is the Laplace transform of cos omega t plus I Laplace transform of sine omega t. And now by applying the left hand side, we got this resolution that the Laplace transform of cos I omega t is Laplace transform of cos omega t plus Laplace transform of sine omega t, which gives me an s square all over s square plus w square plus I, then w all over s square plus w square. If you're very sensitive enough, you'll discover that the Laplace transform of cos omega t, when we compare, okay, real parts and imaginary parts, is going to correspond to the real parts of the Laplace transform of exponential I omega t. So that is the Laplace transform of cos omega t, so is the real parts, and this is going to be s divided by s squared plus omega squared. And the same thing, the Laplace transform of sine omega t is going to correspond to the imaginary part of the Laplace transform of exponential I omega t, and this gives me this value over here. So you have w all over s squared plus omega squared. I call it w, I'm not supposed to call it w, it's actually omega. Okay, so the generalization from this is that when you have the Laplace transform of any sine at, a can be omega, any constant, you will have it in this pattern. So the constant comes here, then divided by s squared, then plus w squared, and the Laplace transform, I'm sorry about that, s squared plus a squared. Then the Laplace transform of cos at is according to this pattern over here. Assuming a is your omega, you have s all over s squared plus omega squared. So you should know this at the back of your head. So I just wanted to introduce this particular system of derivation to you, especially now that you are like a senior undergraduate student. You should know some of these principles. Don't throw away anything that you've learned from 100 level. It's very important. All those complex theories that you learned as your simple trigonometric rules and identities, trust me, you're going to need them even down to your final year. So it's better you keep them at the tip of your finger. So I've used complex numbers apart from integration to show that the Laplace transform of sine at and cos at, where a can be thought of as an angular frequency value, is, in the case of sine at, we have a over s squared plus a squared. In the case of cos at, I made the same mistake, but I'm sure you must have corrected it. Is we have s all over s squared plus a squared. So this is what we have for the Laplace transform of trigonometric identities. So for hyperbolic identities, you can use the same logic. Okay, you can use the same logic in hyperbolic identities. So I'm just going to give you a trick of what you're supposed to do. Like if you have an exponential if you have a hyperbolic function such as sine sine 80, so sine 80, okay, then you now have your cos 80. So the Laplace transform of sine 80 can be solved if you remember your hyperbolic identities. Sine 80 is still exponential. You have 80 and minus exponential minus 80 divided by 2. Cos 80 is exponential 80 plus exponential minus 80 divided by 2. So if you can use these identities on the right hand side, okay, you will be able to find out that the Laplace transform of sine 80, I call it sine 80, some people say sine h, so it's actually going to be a all over s squared minus a squared. Okay, it's going to be like this, but the minus sign. And the Laplace transform of cos 80 is going to give you s all over s squared minus a squared, just like this one, but with a minus sign. So if you can use these identities here, you'll be able to derive it by yourself. But the most important thing is that you should know these forms. Okay, you should know these forms. It is very, very critical and important that you know these forms. So let's move on from trigonometric functions to the Laplace transform of derivatives. So we want to find the Laplace transform of derivatives. So derivatives. So we want to find the Laplace transform of derivatives. So what do I mean? I have the Laplace transform of dy dt, for instance, or dx dt. So the Laplace transform of dy dt or dx dt, whichever one. So in the case of dy dt, we know it as the Laplace transform of y prime. Is that okay? This is going to give you s, then Laplace transform of this small letter y is capital letter Y of s and minus y of 0. So let me explain it. Whenever you take the Laplace transform of dy dt, you're going to get s y of s. Y of s is the Laplace transform of y. Okay, assuming we know what y is. and y of s is usually what you want to find. So sy of s minus y of 0 is an initial condition. If you're, on the other hand, taking the Laplace transform of dx dt, which is the Laplace transform of x dot or x prime, so it is going to be solved using what? You have the same pattern. So you have s. So instead of y of s, you have capital letter X of s and minus x of 0. So this is your initial condition. So normally in mathematics, I just want to tell us something, a secret that nobody will actually tell you. When you have dy dx, it's by convention you should call it y prime, okay? But when you have dy dt, as someone that is into engineering mathematics, it is more professional to call it y dots. So dx dt is x dots. That okay? d2x dt squared is x dot dot. But when you have d2x, d2y by dx squared, d2y by dx squared, you can call it exactly y prime prime. So if the denominator variable is a dx, we use prime. But if the denominator variable is a dt, we kind of like want to use the dot notation for denoting the derivations. So this is the Laplace transform of derivatives. So in another video I would have proved how this formula came about to you, but I just want you to, and let me assume that you know that before, and let me just build on what you already know, because we will never be asked to actually derive at this level. You will not be asked to derive anything at this level for Laplace. You just want to apply Laplace to solving problems like solving differential equations, etc, etc. So you also want to find out the Laplace transform of d2y by dt squared. That's the second derivative. So for the second derivative, you will have that your Laplace transform is s squared y of s, okay, and minus s y of 0 and minus y prime of 0. So for the second derivative problems, you discover that anytime you're given a differential equation in second order, you usually have two initial conditions, your y of 0 and your y prime of 0. Okay, so you will have your Laplace transform taking this form. So you can notice that the power of s is falling from 2 to 1, and if you're very sensitive, you cannot see s, but there is an s raised to the power of 0 in this place. S raised to the power of 0 is 1. Okay, so this is the Laplace transform of the second derivative. So someone might be still be asking, what is exactly is this capital letter y of s? Well, you must have heard of something called Laplace transform pair. So Laplace transform pair is just, in mathematics, when we have like a small letter, okay, when we take the Laplace transform of a small letter, f of t for instance, we usually arrive at a capital letter called capital letter f of s. So normally we call it that f of t is a Laplace transform pair with what? F of s. So under the variable s, that's how we usually call it Laplace transform pair. So the same thing happens. Laplace transform of small letter y of t will give you a capital letter y of s. So we have our y of t is a Laplace transform pair with capital letter y of s. It means that when you take the Laplace transform of f of t, you get f of s, and when you take the inverse Laplace transform of f of s, you get back to f of t. The same thing applies to this one over here. Then the Laplace transform of x of t is going to give you capital letter x of s. So x of t forms a Laplace transform pair, okay, Laplace transform pair with capital letter x of s. The implication is that taking the Laplace transform of x of t gives you capital X of s, and when you take the inverse Laplace transform of capital X of s, you get your x of t. So that is Laplace transform and Laplace transform pairs. So I want to build further for third derivative so that we'll discover a pattern. The Laplace transform of d3y by dt squared. So permit me for this sake to still call it the Laplace transform of, some of us might be used to the y prime prime prime, okay, whatever, or those of us who are used to the y dots dots dots. Yeah, welcome to the world of engineering. So it's still the same thing as s cube. Okay, take note, the s variable takes the power of, that's the order of your derivative, the highest order. So you have s cube, then y of s, then minus, so s starts falling down, you have s squared, and the first initial condition is y of 0, and minus s falls down again by 1 power, second initial condition is y prime of 0, and finally the last initial condition with s to the 0, and it's y prime prime of 0. So this is how you build the Laplace transform of derivatives. Okay, so let me give you this one. So what are you going to get for Laplace transform of d4y by dt to the power of 4? So what are you going to get? So yes, pause the video and try to solve it. Okay, welcome back. I'm sure you paused the video and tried to solve it. So you must have gotten s to the 4 y of s, okay, minus s cube, the first initial condition is y of 0, minus s squared, the second initial condition is y prime of 0, and minus s, you have y prime prime of 0, then finally minus what? Y prime 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 of 0. So if your order is 4, the last initial condition is going to be having like an order of 3. Is that okay? Okay, so this is how we form the Laplace transform. So if I wanted to be consistent with my use of the t variable, I would have had s to the 4, then I have y of s minus s cube, my y of 0, then minus s square, I can have it like y dots of 0, that minus s, you have y dots dots of 0, and minus what? Y dots 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 of 0. So these are, similar symbols, but those of us that are doing courses like control theory, most of the times will find the use of y dots dots and y dots 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 instead of y prime and y prime prime prime. So it's all about flexibility, whichever one you get to use, it's not bad. So I think this is enough for Laplace transform of derivatives. So the most common ones that you're going to encounter in this course is, that's the Laplace transform of y prime, okay, that's the first derivative, and the Laplace transform of y prime prime, okay. So you should know both of them. So for this one, it is s y of s minus y of 0. Is that okay? So for this one, you have s square y of s minus s y of 0 minus y prime of 0. So y of 0 and y prime of 0 are called initial conditions. So whenever you're using Laplace transform to solve differential equation or control system problems, we need initial conditions, very important. So we need initial conditions. So I'm just going to do some random examples before I round up this video. So examples with everything we've learned so far. So examples. So this is just about everything in Laplace transform you need to know, like for engineering problems. Most of the time we have polynomial, exponential, trigonometric, and derivatives to work with. So we'll be doing all of the examples. So if I give you the Laplace transform of 0, that's the first one. Laplace transform of 0 is always 0. So in example 2, the Laplace transform of 1, okay, is 1 over s. Is that okay? So example 3, the Laplace transform of t is 1 over s squared. So remember that the Laplace transform of t raised to the power of n is n factorial all over s n plus 1. So if you're finding the Laplace transform of 1 is still the same thing as t raised to the power of 0. So you have 0 factorial divided by s to the 0 plus 1. 0 factorial is 1. S to the 0 plus 1 is s to the 1, which is s. So the Laplace transform of 1 is 1 over s. The Laplace transform of t, which is t raised to the power of 1. T is still t raised to the power of 1. So you have, according to this formula, 1 factorial divided by s raised to the power of 1 plus 1, which is 1 all over s squared. So you can build on that. Is that okay? So number 4 is the Laplace transform of t cube. So to find the Laplace transform of t cube, still using this formula, I'll have 3 factorial divided by s raised to the power of 3 plus 1. And this gives me a 6 divided by s raised to the power of what? 4. Is that okay? So this is about polynomial functions. So another thing that you may want to remember is for exponential functions. The Laplace transform of exponential 2t is going to give you 1 all over s minus 2 because of this 2 here, since it's positive. So you want to recall that the Laplace transform of exponential at is 1 over s minus a, while the Laplace transform of exponential minus at is 1 all over s plus a. So in example 6, I have the Laplace transform of exponential minus t. So for this one, I can see minus t, which is still the same thing as minus 1t. So you have 1 all over s plus 1. So when it's minus, you have an s plus 1, okay? So s plus 1, and when it's plus, you have s minus 1. So number 7, Laplace transform of exponential minus 2t plus exponential 3t. So apply linearity, and this gives me the Laplace transform of exponential minus 2t plus the Laplace transform of exponential 3t, which is going to be 1 all over s plus 2 plus 1 all over what? S plus s. Is it plus or minus? Thank you for that correction. So it's a minus s minus 3. So you can leave your answer like this, or some of you might want to do LCM. So you have s minus 3 plus s plus 2 divided by s plus 2 s minus 3, and this gives you 2s minus 1 divided by s squared minus s. Then you have minus 6. Okay, so you might be wondering how I did that very fast. So I'll show you the trick later on. So you have to subscribe to my channel, and of course you have to like my videos if you want to see more of my mathematical tricks. I have a lot of mathematical tricks and mathematical cool moves that you're going to like, trust me. So why don't you like this video right now? I need your like. So just go and hit that, respect yourself and hit that like button, please. Ejo Biko, thank you. So number 8 is let's look at the Laplace transform of some trigonometric functions. Laplace transform of sine t. So this is the most simplest. So the frequency, angular frequency, is 1. So I have 1 divided by s squared plus 1 squared, which is 1 over s squared plus what? 1. So this is the Laplace transform of what? Sine t. Now there's something we call inverse Laplace transform. So if they ask you to find the inverse Laplace transform of this guy, then you know it's going to get you back to sine t. But we'll come back to inverse Laplace transforms later. So the number 9 is Laplace transform of cos 3t. So this is going to give me an s all over what? S squared plus 3 squared. According to the formula, this is s divided by s squared plus 9. Is that okay? So what if you have number 10, the Laplace transform of sine root 2t plus cos t over root 3? Okay, this one is a little tough. Blessed, what are you doing? Okay, applying linearity. I'll find the Laplace of this one, which is going to give me a root 2 divided by s squared plus root 2 squared, then plus. So for this one, I have s divided by, I'll have s squared plus 1 over root 3 squared. Is that okay for this case? So you're gonna have a root 2 into s squared plus 2 in this case. Then you now have plus, if you solve this one very well, you're going to have a 3s divided by you will have something like a 3s squared plus 1. So I want you to find out how this one became like this and try to resolve it by yourself. So this is about Laplace transforms for functions. Is that okay? So you should actually know this one very well. So let's go to inverse Laplace transforms. So I'm just gonna touch inverse Laplace transforms briefly and we'll call this video a close. So hang in there. So inverse Laplace transforms. So you must have seen that the Laplace transform of f of t gives us capital letter f of s because of the Laplace transform pair stuff. F of t forms a Laplace transform pair with f of s. Is that okay? So it means that when you take the Laplace transform of f of t, you get f of s. When you take the inverse Laplace transform of f of s, you're going to get f of t. So how do we write that? So the inverse Laplace transform is L to the minus 1 of f of s gives you back your f of t. So for this case, I'm just going to give us some examples. Let's say you want to find the inverse Laplace transform of 1 all over s. So the inverse Laplace transform of 1 over s, where is this coming from? It's actually unity. So when you take the Laplace transform of 1 over s, you get 1. 1 is the same thing as your u of t. That's your unit step function. For those of you in control theory, that your u of t is defined by the function, the branch function 1. That's when t is greater than or equal to 0 and 0 otherwise. Okay, so this is our Laplace inverse of 1 over s. Now another thing that you need to know is the Laplace inverse of 1 over s squared. So this is going to give you 1 over oh, I'm sorry about that. It's going to give you t. Is that okay? So since the Laplace transform of t is 1 over s squared, the Laplace inverse of 1 over s squared is going to give you t. And there is no plus constant of integration. For those of you who are thinking that there will be plus constant of integration, Laplace transform does not have any constant of Laplace shown or whatever you want to call it. So there is no constant. It just gives you the function directly. Okay, so you have the Laplace inverse of 2 all over s cube is going to give you what? Very good, t squared. Okay, so let me be tricky a little. What if I give you the Laplace inverse of 1 over s cube? How are you going to solve it? 1 over s cube. The Laplace inverse of 1 over s cube. This one is very tricky. But I know that the Laplace inverse of 2 over s cube is is t squared. What of the Laplace inverse of 1 over s cube? Well, mathematics helps us to what? Apply the law that energy can neither, matter cannot be created nor destroyed. Is that okay? So this is how I'm going to apply that law. I'll do a 1 over 2, then Laplace inverse of 2 over s cube. Something like this. So 2 can actually cancel out these 2, you understand? That's why I introduced it in this way. So whatever you're introducing in the numerator, be sure to introduce it in the denominator. So this gives me 1 over 2, and Laplace inverse of 2 over s cube is actually what? t square. So this is a t square over 2. So t square and half is the Laplace inverse of 1 over s cubed. Okay, let's generalize what we have learned about inverse of this form. So Laplace inverse of 1 over s raised to the power of n. So what's it going to be? So you have to be very smart in calculating problems like this. So you have to recall that the Laplace transform of t raised to the power of n generally is n factorial over s raised to the power of n plus 1. So I'm going to do some manipulations and I want you to flow with me. The Laplace inverse of 1 all over s raised to the power of n is going to you can still calculate it in this way. First of all, I'm going to divide by an n minus 1 factorial in this way, and Laplace inverse of n minus 1, okay, factorial divided by s raised to the power of n, like this. So if I follow it in this way, what am I going to get? If you are very sensitive, this and this is kind of like the same thing. It's kind of the same thing, but the only difference is that the order of t now has now been reduced by 1. So in this case where we have t raised to the power of n, I have n factorial. But if you compare this to this, you agree with me that this should not belong to a t raised to the power of n, rather it should belong to what? It should belong to a t to the n minus 1. So like this. So the answer is 1 all over n minus 1 factorial. Then you now have t raised to the power of n minus 1. Okay, so the Laplace inverse of 1 divided by s raised to the power of n is 1 over n factorial t raised to the power of n minus 1. So you should memorize this, or you should learn how to derive it, whichever way. Please just make sure you have it at the tip of your fingers. So applying this formula to Laplace inverse of 1 over s cubed, like we solved above, according to the formula, I have 1 all over 3 minus 1 factorial. Then you now have t raised to the power of 3 minus 1, which is t raised to the power of 2 all over 2 factorial, which is t square all over 2. So back to where we were coming from. Okay, up here. So I hope you're learning. So this is about Laplace inverse of these functions, polynomial. So how about exponentials? Laplace inverse of something like 1 all over s plus 3. So definitely this takes me back to exponential negative 3t. Remember that the Laplace transform of exponential 8t is 1 over s minus a, and the Laplace transform of exponential minus 8t is 1 over s plus a. Okay, so this should give me my answer. The Laplace transform of 1 all over s minus 2 is going to give you an exponential 2t. Is that okay? So please try to remember this. So the Laplace transform of a function, for instance, you have s. Let's say you have something like okay, let me see what I did initially. I want to see what I did initially in this place. What did I do for this? Okay, I had these two right over here. So this is what I got in this case. So let me try to find the inverse Laplace transform of this one. So just give me a second. 2s minus 1 all over s square minus s minus 6. So follow. So we have Laplace. I've not been putting inverse. Oh, I'm sorry about that. Just some little mistakes in mathematics. The Laplace inverse of 2s minus 1 all over s square minus s minus 6. So when you have something like this, what are you going to do? So you have to remember partial fractions. So Laplace transforms and Laplace inverse transforms and partial fractions, they are like 1 and 2. So you might want to refresh yourself on partial fractions, different methods of partial fractions. But in this course, as I'm going to be showing you like cool methods that you can use, and hopefully it will refresh your memory. This is how I was going to solve this problem if it were me. I'll first of all say consider the fraction 2s minus 1 all over s squared minus s minus 6. So if I say 2s minus 1 over s squared minus s minus 6, I want to break it down into, first of all, its partial fractions. When you're given a complex fraction in this form, you need to break it into its partial fraction before you find the Laplace inverse of that fraction. So it's still the same thing as you saying 2s minus 1 all over. First of all, if we factorize this, I can see s and I can see s, two numbers that I multiply to give me minus 6 and that I add to give me minus 1. That is definitely a plus 2 and a minus 3. Plus 2 times minus 3 gives you what? Minus 6. Then plus 2 minus 3 is minus 1. So I have an s plus 2 and s minus 3 over here. So this becomes, according to the laws of partial fraction, I will have a all over s plus 2 then plus b all over s minus 3. Okay, so this is my fraction. I want to find the value of a and b. I'm going to teach you cover-up method. Cover-up method is useful. You can use method of comparing coefficients, but when you have linear factors in your denominator, use cover-up method. So for cover-up method, if I want to find a, what I'll just say is a is the limiting value as s tends to what? What is s tending to? Now look at this particular denominator in a. It's s plus 2. So if I want to find the root of this s plus 2, I'll equate it to 0. S plus 2 equal to 0. That means s is equal to minus 2. So s will tend to minus 2 in this case. So how do I apply this limit, and where do I apply this limit to? I'll apply it to this left hand side, only that I'm going to cover the denominator of a, which is s plus 2. That's why the name comes from cover-up method. So you have 2s minus 1 divided by, instead of you to have s plus 2 and s minus 3, you have only s minus 3. So you've covered up what you've covered up the factor belonging to a. So if you evaluate this limit by direct substitution, you have 2 into minus 2 minus 1 divided by, you have minus 2 minus 3. So this gives me what? It gives me minus 5 over minus 5. Is that okay? And in that case, a is 1. So another thing that you need to do is you need to use the same technique to solve for b. Is that okay? So let's solve for b. So to solve for b with cover-up method, you have b is the limiting value as s tends to what? So if you solve this particular denominator by equating it to 0, you're going to get 3. So s minus 3 equal to 0, meaning s equal to 3. So applying this limit, you apply it to the left hand side, then cover up that linear factor, that's s minus 3. So you have 2s minus 1 divided by what? S plus 2. So this gives me 2 into 3 minus 1 divided by 3 plus 2, which is a 5 over 5, and b is 1. So the value of a and the value of b is 1. That means this 2s minus 1 all over s square minus s minus 6 evaluates to 1 over s plus 2, then plus 1 over s plus 3, okay, according to what we have over here. So remember that we're finding the Laplace inverse of this fraction. So that means the Laplace inverse of this fraction is the Laplace inverse of the sum of these two fractions. And Laplace inverse also obeys linearity. So the Laplace inverse of the sum of two things is the sum of the individual Laplace inverses, okay, plus Laplace inverse of 1 over s plus 3. So at the end of the day, the Laplace inverse of this complex function, which is 2s minus 1 over s squared minus s minus 6, is still the same thing as your Laplace inverse of f of s, okay, because this is your complex f of s, a function of s in terms of s, and the Laplace inverse of 1 all over okay, I think I missed something. Okay, yes, thank you for the correction. So this is s minus 3, not s plus 3. Sorry about that. So Laplace inverse of 1 over s plus 2 gives you it gives you, of course, exponential minus 2c. Is that okay? And plus the Laplace inverse of 1 all over s minus 3 gives you exponential 3t. So we have gotten our f of t. So the Laplace inverse of f of s gives you an f of t in this form. And if you look very carefully, this was the same thing that we got when we took the Laplace transform of that function over here, right? When we took the Laplace transform of this function, we got this variable. So these are f of t and this is our f of s. So when we took the inverse from f of s, we have now arrived at what? F of t. So there are many times that your partial fraction will lead you to finding the inverse Laplace transform that will land you at trigonometric functions, and trust me, you're going to see most of those examples. So just refresh partial fractions, okay, if you're not very strong. Refresh cover-up method, refresh comparing coefficients. Method of comparing coefficients is very important. Then yeah, just refresh most of those methods of completing the square. You can use it to find inverse, and I'm going to show us that in some future example, or like the example we saw in the first video that I released on Laplace transform. I used that method of completing squares and cover I didn't use cover up method, but I used method of comparing coefficients. I call method of comparing coefficients leap of faith. So you have to be very bold when you're using method of comparing coefficients because of errors. It's prone to a lot of errors if you cannot see very clearly. But if you take that leap of faith and if you're very careful, you're going to resolve your answer very perfectly. So I guess this is about Laplace transforms. When you are given a function like this, Laplace inverse of something like s all over s square plus, let me see, 7, and you want to find the inverse Laplace transform of this, so you should recall that this looks like the cosine form, that the Laplace transform of cos 8t is something like this, s over s square plus a square. So the only problem with this one is that I can't see a square here. But who says I can't see a square? I can actually manufacture a square like this, s all over s square plus root 7 all squared, so that this translates to what? Cos root 7t. So this is how you treat Laplace transform and Laplace inverse. So I'm just showing you this video so that you can be very versatile when you are attending to questions involving Laplace transforms. I hope you've learned a lot from this video. Please don't forget to like and to subscribe and to share. Hit the notification button so that you can stay updated on future posts.